Hello everybody, this is going to be a very quick video over perceiving machines and neural mind reading. So, one way that we can understand how our perceiving machine works is by creating software programs that we train to perceive on their own. All right, and so that that allows us to essentially test whether or not the way we think the perceiving machine works. Specifically, if we think our perceiving machine works in one way, then we can make a machine that works in that same way. If it then works, that tells us something about how accurate we are, about how our perceiving machine works. And our perceiving machine is freaking awesome. All right, it accomplishes some great tasks. For example, the distal stimulus, all right, the things that we're perceiving out there in the environment, like the light being reflected off this plant in my office, all right, when the image that reflects off of that plant lands on my retina, that image on my retina, that's the proximal stimulus. Now here's the cool thing, and it's a little scary if you think about it a little too much. That proximal stimulus on my retina can be created by an infinite number of distal stimuli, not just the one I think is there. And so our perceiving machine has to do this guessing game of, okay, this is what's on my retina, these are the things I've seen in the past, and so the thing on my retina right now must be, in the case of this, my plant in my office window. All right, but my perceptual system is having to make a guess, and that's how we think our perceptual system is working right now. But one way we can test all the models about how we think our perception system is working is by, again, making computers that work in those same ways and seeing if those can do the job. Now, one way that we can create a perceiving machine is by first looking at how our brain reacts to specific stimuli. So we can show people an image, like, for example, an image of a grating, like you see here. All right. So we can show participants something like this, and then see how their brain is active. Well, we can also, because the brain is a 3D object, we can break the brain up. We can into small regions, very small regions, and then look at the activity in each of those small regions. And that can create an fMRI image. And each of these small regions are like a 3D pixel or a voxel. All right, so they're a small segment that have volume. All right, so a voxel, whoop, like you see there, or voxels is plural. All right, a voxel is, you can think of it like a 3D pixel, but it measures the activity in a very small region of the brain. And so if we show them this and we see this pattern of activity, then we can train our computer program to recognize, hey, this pattern of activity is associated with this image. And we can show them a bunch of different images that all vary from this in a certain way. And then we can have the computer program learn what pattern of activation across the small regions of our brain are associated with each of those images. Then, and the reason we know, we know what they're seeing because we're showing it to them. We can then show them a random image that we don't actually know. Obviously, we would preset what the images are, but we could then show the individual a random image pulled from one of hundreds maybe. Then measure their activity in their brain, give that information to our computer program, and then see if the computer program can accurately guess what they've been seen or what they've been shown. All right, and if it can, then it's essentially reading our neurons. It's reading our neural activity. It's neural mind reading. All right, and so in this case, it's very simplistic because the image is very small. But most of the images we see on a daily basis are far more complex. You know, for example, we might see, and we do see, all right, things that vary, like you've got landscapes, people, objects, like the cacti here. So we see very complex objects. Well, we can show people even complex objects like this, and then look at the activity in each voxel and see what patterns of activity across those voxels, those 3D pixels, are associated with each image. But there are different features of each image that we could train our program to code for, such as structural features. All right, so for example, this is very flat. It's got a rise back here. This, you got a white area up top, and you've got kind of this curve in the middle here. All right, this one, it's entirely full, but you've got these circle-ish or spherical looking objects here. So those are structural features. These are patterns. These are shapes in the image. Which we could also have and so, well, before we move on, so what we could do is we could show participants each of these images and many more images that vary in these ways, and look at the activity in each voxel throughout the brain. We could then tell the machine, okay, so this pattern of activity is associated with this image. This next pattern of activity is associated with this image, and this next pattern of activity is associated with this image, specifically focusing on the structural features. So this pattern of activity is associated with these having multiple spherical structures. This pattern of activity is associated with a person. All right, this or not, no, sorry, not a person, but having, you know, this small lump here, this structure, a kind of a curved structure here, an area of black surrounded by areas of kind of paler. And then this is this pattern of activity is associated with kind of a dark area on the bottom, bright area on the top, and then kind of a curved border between the two. Those are all structural features. Well, that program would then learn what patterns of activity are associated with these structures, what patterns of activity associated with these structures, and what pattern of activity is associated with these structures. Well, we could also make our program encode semantically, meaning we could tell our program that, hey, this pattern of activity is associated with seeing a small clump of cacti. This pattern of activity is associated with seeing a person on a merry-go-round. This pattern of activity is associated with seeing a landscape. All right, specifically a landscape with a hill in the back. So our computer program would then know, okay, well, we know what patterns of activity happens when people see structures like this and what happens when people see cacti. The program could say, well, I know what pattern of activity is associated with these structural features and what pattern of activity is associated with seeing people. And our computer program would know what patterns of activity are associated with landscapes, or not landscapes, landscapes is semantic, but with a brighter area up here, darker area down here with a curved edge, and our program would know what pattern of activity is associated with landscape. Well, then we could randomly show people other images that they haven't, that the computer program has never seen before. And so, because the computer program will have never seen those images before, it can't accurately guess, but it can make close approximations based on what it's learned. And so we see what can happen. So we can show a person this, measure their activity, feed that information into the machine, and then if the machine is basing its guess solely on the structural features of that image, then these are the guesses that it might make. And you can see, structurally speaking, these are pretty close on, but not, well, I guess those are buildings, and I guess there's some buildings in the background here. So there are some semantic features, but that's not what it's coding for. It's coding for the structural features. And so in each of these, you've got this kind of swooping structure. Well, if we have the program instead try to guess what the target image based on both structure and semantic features. So yes, there's the structure here, right, where you have a different colored area here, areas up here that seem to be closer, and even where you have area, part of the lower part of the scene is brighter than others, and the semantic piece, sky, building, then it gets even closer. So for example, its most probable image, sky, building, even the structural features of the building are still there. All right. It apparently even identified the trees back here that are hard to see in the target image, but they're here. Now, these are less probable, and they're less like the target image. So the computer program did a decent job. Now again, I'll reiterate, the computer could not have come up with the right image because it didn't have the right image in its database. So it couldn't have figured that out. So it couldn't have come up with the exact image. What the researchers were hoping to find is whether or not, if we can train a program to code based on semantic and structural features, can the program read the mind, neural mind reading, of a person and figure out what structure or what thing they were shown. And when guessing based on both semantic features and structural features, it does a pretty good job. Now, that gets us back to that first piece, which we can learn more about our perceiving machine by creating machines that work in a way similar to the way we think our perceiving machine works. And if it does the job, that tells us that we're on the right track with figuring out how our perceiving machine works. The fact that a machine that uses structural and semantic codes to identify a structure, and that it does pretty well, better than when identifying on structure alone, the fact that the machine can identify the structure pretty well based on both of those tells us that when we think that we identify objects by using scene schemas and physical details or physical regularities of the scene, the fact that we can get a computer that works based on those principles to do a pretty good job of identifying or guessing what a scene is, that tells us that we're probably on the right track in our understanding that our perceptual system is guessing what we're seeing based on physical regularities and semantic information like that we have stored in our scene schemas. And that is that. All right, guys, that's my talk about neural mind reading and creating perceiving machines. As always, if you have any questions, please send them my way. If not, I'll see you later.